Hello, students. Mr. Kaczynski with you yet again. We're going to do the 3.5 reason and apply problems together. So what I want you to do right now is pause the video, attempt problem number 5, all parts of it, and then when you're done, press play, and I'll take a go at it. All right, go for it. All right, here we go. We got a bunch of different input-output relationships. X for input, Y for output. Inputs are independent variables. Outputs are dependent variable. Find the rate of change for each value in the table. Explain how you found this. All right. Yeah, so, I mean, I think it's going to be pretty clear that we could just do the difference in the outputs. Difference means subtraction, not division. So negative 2.5 minus 6.5 minus negative 6.5 is 4. Okay. Be careful too, because we have to look for the input change and make sure it's 1. If it's not, we have to divide by that. But 4 divided by 1 is 4. So now I'm going to use a recursive rule to kind of check things out. Negative 6, enter, plus 1, or plus 4 rather. What just happened? Why did I say 4? Oh, because I typed it in wrong. All right, so let's try this again. I don't want a mistake right off the bat. Obviously, I should be using mental math instead of a calculator because it messes me up. But minus negative 6, not negative 6.5. That's 3.5. Slow your roll, Kaczynski. Okay, so here we go. 3.5. Now let's use our recursive rule and check things out. So we've got negative 2.5, enter, plus 3.5. That gives us the negative. My gosh, negative 6. My brain's fried. I've done a lot of stuff today. Plus 3.5. There we go. That gives us the negative 2.5, then the 1, then the 4.5, then the 8. Okay, we're almost done. Part A of the number 1 here. My gosh. All right, so it's 3.5, right? All right, now what about 2? Let's do this faster this time. Obviously, that's an increase of 8. And this went up 1. Check it, negative 7, enter, plus 8. That gives me the 1. Oh, see, that's for input 1, then 2, then 3, then 4, then 5, then 6, then 7. So we kind of got to be careful here, because even though this is an increase of 24, that doesn't mean it's not linear. This was an increase of 3, and 24 divided by 3, of course, is 8 again. And this is an increase of 16, but that's because our inputs went up 2, and obviously 16 divided by 2 is also 8, so our constant rate of change here is 8. All right, what about 3? Oh, kind of ugly here. Maybe I just go down here to the positive numbers. Okay, 11.8 minus 20.2. That's negative 8.4. But 8 from 2 is an increase of 6. So negative 8.4 divided by 6. It should be that our rate of change is negative 1.4. We'll check that with the recursive rule. 34.2, enter. Minus 1.4. That should give us 32.8. And then for negative 6, negative 5, negative 4, negative 3, 27.2, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. There we go. We got them all. All right, for each table, find the output value that corresponds to the input value 0. What is it called? It's called the y-intercept. Okay, so for 1, we can clearly see it's negative 6. For 2, we can clearly see it's 1. And for 3, I went right past it when I was doing my recursive rule, so we're going to have to do it again. How about we just start at negative 3's output, which is 27.2. We subtract the 1.4. That'll give us the output when the input is -2, then -1, then 0. So 23 is our output, our y-intercept there. Y-intercepts. Use your results from 5a and 5b to write equations for each one. All right, so 1, y equals -6 plus 3.5x. And 2, y equals 1 plus 8x. And 3, 23 minus 1.4x. Oh, I got my y equals, didn't I? I don't want to be lazy. I'm going to put it in. Y equals 23 minus 1.4 times x. Oopsie. And then lastly, use a calculator list of input output values to check that each equation actually produces the output value shown on the table. So we're going to go to y equals, we're going to put all three of these equations in at the same time. -6 plus 3.5x, put that in y1. And then we're going to do 1 plus 8x, we'll put that in y2. And then we got our 23 minus 1.4x that we'll put into y3. Go to our table by hitting second graph. And let's see. For y1, I got my 0, -6, my 1, -2.5. There's my 1, the 4.5, and the 8. For y2, we got our, I got to go up to -1. So -1, -7, 0 and 1, 3 and 25, 5 and 41. And then for number 3, I got to go up here to -8. There's my, something's not right there. It's supposed to give me 34.2. Oh, I see what's happening here. 3 minus 1.4x. What did we mess up? -8.4 divided by 6 is -1.4. Check my recursive rule, 34.2 minus 1.4, that gives me -7. -6, -5, -4, -3, -2, -1, and 0. Should be 23 minus 1.4. Oh, I know what I'm stumped. You guys are probably yelling at your computers right now what I did wrong. -23 minus 1.4x. 23 minus 1.4 times 8. 23 minus 1.4 times 2. Giving me the right values. So why is this not working? Clear these other ones. Try to re-enter. This does not make sense. My 23 minus 1.4x. Going to my table. There's the 34.2. Why the heck was it showing -63? All right, we got it, right? I don't know. All right, we got it. Number 6, your turn. Go. Pause it. Don't worry about the in-out game on your calculator. All right, let's write these equations here. Y equals, what's my y-intercept? That is 7. What's my rate of change? That is 4. Every time x goes up 1. So we're going to write plus 4x. These are actually easier than the last one. And I see 28. So we're going to say y equals 28. Rate of change. Let's make sure. Is this minus 11 when x goes up 1. So minus 11x. And then the last one, y equals, again, they give us the y-intercept. It's got to be paired with that 0. It doesn't have to necessarily be the first pair in the table. It's got to be paired with the 0. What's happening here? I see an increase of 8 every time x goes up 1. Plus 8x. And instead of checking with a calculator with the y equals function of the calculator, I'll just do 7 plus 4 times 2, and this should give me 15. 2 and 15. Second, enter. Oops. I could change the 2 to a 4, and it should give me 24. There we go. Uh-oh. Yeah, I remember this one, because the last one goes up 5. That should be 23. I think that's just a misprint. But I did that. I remember that. All right, next one. Let's do this again. 28 minus 11 times 4 should give us negative 16. And times 1 should give us 17. It does. Let's try it with a graph on this last one. Let's go negative 4 plus 8x. Zoom 6 for a standard window. Trace 0, negative 4, yeah. 1 and 4. 2 and 12. 3 and 20. 4 and 28. Yeah, so we got a right answer. Okay. Next, you're going to pause. You're going to try number 7. Unpause when you're done, and then I'll try. All right, here we go. Find the input and output values. Input, temperature, output, variables. And input, we'll call it input X. How about that? Temperature, output Y. And chill. Okay, so those are our variables. This is for 35 mile per hour wind speeds. Find the rate of change. All right, careful. This one's a little tougher. How about this? I see a change of 21 when this went up 15. Okay, so back to my home screen here. 15, nope. 21 divided by 15, excuse me. 21 divided by 15 is 1.4. All right, let's do that again. How about this increase of 14 when this went up 10? Okay, so that's obviously 14 divided by 10. I don't need a calculator for that. That's 1.4. So our rate of change is definitely 1.4. So explaining how I got my answer, I'm going to say it. I divide the change in the inputs by the change in the outputs. Write an equation in intercept form. Got it. Y equals, you know what? I don't see my 0 value though. It's right in there, right? So how about I use a recursive rule? I go negative 5, enter, plus 1.4. That gives me negative 4, negative 3, negative 2, negative 1, 0. Just 2. Let's keep that going. 1, 2, 3, 4, 5. I messed up. That's not right. Get out of there. It's supposed to be minus 1.4, isn't it? No. No, it's 1.4. Because then you start at negative 35. My brain is fried. Plus 1.4. So that's negative 4, negative 3, negative 2, negative 1, 0, which is negative 28. Now that fits the pattern a lot better, doesn't it? So negative 28. And then we've got 1, 2, 3, 4, 5. Yep, negative 21, 6, 7, 8, 9, 10, negative 14. Okay, so there we go. Plus the 1.4 times x. Boom, got our equation. Plot the points and graph the equation on the same set of axes. How are the graphs for the points in the equation similar? Are they different? Well, okay. Stat, enter, clear those, clear those. We got our negative 5, 5, 10, 20, 35. We got our outputs at negative 35 and negative 21, negative 14. This is just making you guys think about wanting a cold day, isn't it? Day off school. All these wind chills. All right, let's turn our scatter plot on. Check our window. We'll go from negative 10 up to 40 for temperatures and for wind chills. Scale that by 5s. Wind chills, let's go from negative 40 up to 30. Scale that by 5s as well. Y equals, put our equation in there, negative 28 plus 1.4x. Graph. So there's our scatter plot and our line. Okay. Are they the same? How are they different? Well, how about this? They both, both the scatter plot and the equation, also known as the line, have the same slope, but the equation, again, line is continuous and shows all values of temperatures and wind chills. Doesn't skip from value to value. All right, we got a couple more. Hit pause, try number 8. Samantha and Darren's walks are recorded by a motion sensor. Each walk is represented here. Write an equation for each walk in this form. All right. So our distance is going to be. Let's stop using x and y. How about we use d and t? Let's do that. All right. So let's go Samantha. Abbreviate her. We're on first name basis, nickname. So we're gonna her distance is equal to 4 minus 0.6. Nope, that's not right. 0.3 times t. Where did I get the 0.3? Because this is a decrease of 0.6, but that is over not 1 second, but 2. And this is a decrease of 1.2, but that is over 4 seconds. Oops, 2. That's over 4 seconds. So let's go here. Negative 0.6 divided by 2 is negative 0.3. Negative 1.2 divided by 4 is also negative 0.3. Okay, so there's Sam. My boy Darren. This is not a good mouse to write with. His is distance equals. I gotta erase this stuff. I can't see his y-intercept. I'm gonna call that 3.5. Right there. 3.5. He's also walking towards the sensor. So minus, because the line's going down. How about, that one seems pretty clear. 1, 2, 3, 4, 5, 6 seconds. 1.5. So he traveled down 1.5. I'm going to make that negative over 6 seconds. Negative 1.5 divided by 6 is negative 0.25 times t. All right, if Samantha and Darren keep walking at the same rate, which will pass the sensor first? So let's go to y equals. Let's put our equations in. Let's get rid of that scatter plot. 4 minus 0.3x and 3.5 minus 0.25x. Let's go to the table. And let's see, 1 second into their walks. How about 2 seconds in? 3.4, good. 2 seconds in, and this person's at 3. That's right. How about 6 seconds in? This person is at 2.2. Samantha is, and he's at 2. So our equations are definitely right. So Samantha's 2.2 away, and Darren's 2, and 1.9 and 1.75, 1.6 and 1.5, 1.3 and 1.25. They're both 1 meter away. So since at this point, 10 seconds in, if they're both 1 meter away, now the faster person is going to get there first, and that's Sam. Yeah, and it's going to take Sam. Yeah, she's already passed it before the 14th second, whereas Darren's hitting it exactly at the 14th second. So Sam takes just under 14 seconds to reach the sensor, and Darren takes exactly 14 seconds to reach the sensor. It was a close one. All right, last one, 19, or number 9. This is all you. And then you get the review for homework. Okay, pause it, try 9. Here we go, last one, and I'm done making 6 videos, 3 for Math 8 and 3 for Algebra. You can use the equation 7.3 x equals 200 to describe a rectangle with an area of 200 square units like the one shown. What are the real-world meanings of the numbers? Oh. The numbers and the variable in the equation. Okay. Let's try, let's just type this out, okay? 7.3 is the width of the rectangle. X is the length of the rectangle. And 200 is the area of the rectangle. And length times width equals area, doesn't it? Or width times length in this case. All right, so all we got to do is divide both sides by 7.3. 200 divided by 7.3 gives us that x is about, how about this? Can I go math? It's about 27.4. Math, enter. It's exactly 2,000 over 73. Okay, is it drawn to scale? Absolutely not. Okay, so 27.3 is about 4 times 7.3. 7 times 4 is 28. So this rectangle is not drawn to scale because its length is way more than 4 times its width. How about that? And I am done. And you are done with reason and apply. So go ahead and work on the review exercises. Have a good one.